Hi everybody, I'm going to present my paper SecWIR Securing Smart Home IoT Communication via Wi-Fi Routers with Embedded Intelligence. IoT devices are increasingly popular in home. Among different IoT communication technologies, Wi-Fi is the most popular for home use. A recent report says that it will reach 17 billion in 2013. So in this paper, we focus on studying and guaranteeing the security of IoT communications because it is fundamental of IoT security. This is the commonly used Wi-Fi IoT service model. The IoT devices are controlled by the vendor-specific IoT applications installed on a smartphone. We have an empirical study on 40 best-selling IoT devices on Amazon spanning 4 categories: remote control, automation, appliance, and security. We have 2 main findings. First, 23 of them do not support any security protocols. Those devices is referred as non-SIC IoT devices. And 6 of them are not compliant with security protocols. For example, they have flawed certificate validation. They are referred as in-SIC IoT device. Based on the detected vulnerabilities, we can perform various man-in-the-middle IoT attacks. The first attack is hijacking attacks. We can turn on or off the victim's smart plug. The second attack is spying attack. We can spy the victim from a smart camera. Are IoT vendors simply ignoring security issues in their products? No, the situation is far more complex. Most IoT vendors support security protocols for their communication between IoT smartphone control application and the IoT servers, but not for IoT device and IoT server. There are 2 possible reasons. First, Wi-Fi connected IoT devices leak the resources. Second, not all IoT devices support remote software firmware updates. The existing solutions can be classified into 2 categories. First, the device-based approach requires aftermarket IoT device to patch, so they may not be suitable for weak IoT device. Second, the infrastructure-based approach requires users to purchase additional secure hardware. The cost may deter users to adopt it. Therefore, secure IoT devices without requiring aftermarket updates and the purchase of additional secure hardware is challenging. We propose SecWIR to provide secure IoT communications through commercial off-the-shelf Wi-Fi home routers. There are 3 key benefits. First, the home Wi-Fi router represents an ideal chunk point to deploy a solution. Second, SecWIR leverages the existing home routers so the deployment cost is reduced. Third, it offers substantial benefit to both IoT vendors and IoT users. The design of SecWIR is challenging. First, Wi-Fi routers are heterogeneous. Not all of them have sufficient resources to support IoT secure functions, especially for low-end routers. Second, Wi-Fi routers are designed to routing packets. It is challenging to design solutions that can provide secure functions will not influence the performance of routing. From this figure, we can see that if there are SSL connection traffics, then the routing performance will downgrade. We propose 4 novel mechanisms for making more efficient use of the router resources. First is IoT-specific tunneling. Only allow non-SIC IoT device to use the secure IoT communication. Second is priority-based tunneling. It adopts priority-based tunneling management algorithms to provide non-SIC IoT device with secure IoT communication while largely preserving user experience. The third is stream security validation. is secured in SecIoT device using a lightweight stream processing approach. The fourth is resource monitoring. It monitoring the resource usage and dynamically assign resources to SecWIR. We make three assumptions. First, IoT device vendors are willing to secure their IoT devices. Second, IoT vendor realms in which the IoT servers are deployed are secure. Third, the owner of the IoT devices has at least one Wi-Fi routers which support Wi-Fi protected access protocols. We want to ensure two security guarantees. First, the security of all IoT traffic exchanged between the IoT device and IoT vendor. The second is integrity of the IoT traffic. A secure IoT communication consists of three passes: 1, 2, 3. SecWIR arm to provide security communication for pass 1 and pass 2. For pass 1, SecWIR using the Wi-Fi encryption protocol to provide secure communication. For pass 2, SecWIR establishes a secure tunnel between them. All IoT devices coming from the same IoT vendor will share an SSL TLS tunnel. SecWIR employs two mechanisms: IoT-specific tunneling and priority-based tunneling management. The priority-based management has two design principles. First, the priority of the tunnel is determined by the highest priority among the IoT devices sharing it. Second, the higher frequency used IoT devices are granted with higher priorities. There are two approaches to detect IoT device access. The first is traffic outlier detection. It can detect foreground and background IoT access, and cross-application detection. It can detect foreground IoT access. There are three states of tunnels. The active tunnel means that the tunnel has not been established and can be used for transmission. The inactive state means that the tunnel is suspended and can be recovered by using session resumption. The waiting state means that the tunnel has not yet been established. The state transition is controlled by the algorithm shown here. The stream security validation module examines whether the communication establishment is compliant with security protocol standards. The existing tool has two limitations. First, it does not support stream processing. Second, the existing tools are not optimized for our purpose. There are two components. The security standard validation validates the received server certificate. It can examine whether an insecure algorithm is used, and guaranteeing that the IoT device cannot communicate with the IoT server before the validation is finished. The hash added validation can cache the certificate hash and to use that hash to accelerate the certificate validation process. SecWIR supports two security guarantees: security and integrity over pass 1 and pass 2. In pass 1, it is protected by Wi-Fi security protocols. In pass 2, it is protected by SSL, TLS security protocols. We discuss how SecWIR defend possible attacks. The first kind of attacks is attacks launched inside home Wi-Fi routers. First, the IoT compromise DOS side-channel attacks. The IoT device must suffer from various forms of internal attacks, including compromising attack, DOS attack, for example, pin flood. The solution is that the IoT devices are prevented from communication with any internal host other than SecWIR. The second attack is IoT masquerading attack. Adversary must spoof a MAC address of the authentic IoT devices, and then send a large quantity of spamming traffic to the IoT server, thereby exhausting its resource. Our solution is that SecWIR IR can detect the attacks by using the Unicode security key, pairwise transit key associated with each device. The third attack is malicious compromised IoT attack. A compromised IoT device can gain the access to the shared channel and may overwhelm the kernel to hurt the performance of the other IoT device. The SecWIR can protect the IoT device from being remotely compromised. For physical compromise, the attack can be mitigated by employing a per-device rate limit mechanism. The fourth attack is the delay of IoT service attack. Adversary may compromise the victim's non-IoT devices and then use those devices to generate a huge amount of non-IoT data traffic to consume the resource of the home Wi-Fi router. Our solution is that the SecWIR can assign a small amount of guaranteeing the resource. Second, the SecWIR can use file bandwidth sharing technologies provided by Wi-Fi router. We now analyze how SecWIR defend attacks launched outside home Wi-Fi. The first attack is SSL TLS protocol attack. The above attacks make use of insecure algorithms and problematic implementations. Hence, they can be defended by using proper cipher suite and have proper implementations. In side-channel attack, adversary can infer users' IoT usage by analyzing the encrypted IoT data. Inferring a particular device is hard in SecWIR since multiple IoT devices share a TLS kernel. Second, additional noise can be introduced by SecWIR. SecWIR is implemented using OpenWRT project. It is a Linux operating system targeting embedded devices. It enables us to develop solutions on Wi-Fi routers. Currently, this project supports more than 1,000 different Wi-Fi models. We implement 3 modules. The IoT Secure Tunneling module uses Open SSL library to establish, close, and restore SSL TLS tunnels. The Streaming Security module has 7 routines to check the validity of the IoT server certificate. The Resource Monitoring module using top commands to retrieve CPU and RAM usage. The evaluation consists of 3 parts. First, we evaluate the SecWIR secure functions. Second, evaluate the SecWIR overhead. Then we compare it with the commercial IoT secure gateways. The experimental testbed is described on this figure. We tested the IoT secure tunneling while using 8 IoT devices. Our results show that the IoT secure tunneling is successfully established. We also launched 2 attacks towards the module and found that SecWIR can detect those 2 attacks and prevent the communication between the insecure IoT server. We evaluate the overhead of SecWIR by following metrics. First is extra IoT access delay. 2 types of access are considered: foreground and background. Foreground means the IoT access command, and background means, for example, the keep alive message. Second metric is non-IoT data throughput downgrade. 2 types of non-IoT data services are considered: on router, for example, the FTP, iTunes, DLNA data services, and off router, for example, accessing internet from the user's laptop. The third metric is RAM usage. The fourth metric is CPU usage. We also compare the overhead of SecWIR with those secure IoT communication solution and the baseline SSL TLS tunneling scheme. We evaluated the CPU and RAM usage of the IoT secure tunneling module. We find that the maximal RAM usage is 2.7 megabits and the maximal CPU usage is 4%. Our solution takes 2.7 megabits to support 1,000 IoT devices, whereas the basenet algorithms can only support 15 IoT devices. The extra IoT device access delay is less than 200 milliseconds, and it is unlikely to be perceived by users in use. The resource monitoring module can control the throughput downgrade less than 8% by slightly trading off extra access delay. We also evaluate the stream security validation module. We have 3 observations. First, the Hashi-added circuit validation process results in a lower extra IoT devices access delay. Second, the Hashi-added validation process has only a small effect on the throughput of the Wi-Fi router. Third, the validation module does not impose any significant performance overhead when securing SecIoT device. We also evaluate SecWIR on 5 low-cost Wi-Fi routers. From our experience, we find that the maximal access delay is less than 200 milliseconds. The maximal throughput downgrade rate can be controlled under 8%. The RAM usage and CPU usage is not too much. In summary, our solution is highly efficient. We also compare our solution with the Samsung IoT Secure Gateway. There are 3 advantages of our solution. It has wider supportability, lower deployment cost, and no extra hardware is required. In summary, this paper makes 3 main contributions. First, an investigation is performed on 40 popular IoT devices. Second, SecWIR can be deployed on commercial off-the-shelf home Wi-Fi routers. Third, SecWIR can let IoT users to enjoy inexpensive but still security IoT device with high performance. Thanks for your listening. Any questions?